Chemical equations and reaction stoichiometry. Here's where we learn to write chemical equations, and stoichiometry is all about the math of chemistry. That is, how much reactant, how much product are going to be involved in a reaction. Chemical equations basically are representations of chemical sentences. On the left-hand side of our representation are the reactants, which are generally the species, chemical species that is, that are consumed. On the right-hand side of the arrow are the products. These are generally formed in the reaction. So there are two ways of looking at this. First of all, we can read the following equation as a sentence. Ammonia reacts with hydrochloric acid to produce ammonium chloride. Or we can do the opposite. We can take a sentence and convert it to an equation. A reaction of hydrogen with oxygen makes water. However, there's a problem with this last one, and that is it is not balanced. As you can see on the left-hand side, there are two oxygens, and the right-hand side, there's only one oxygen, and that is the first thing that we have to work with. State symbols. S is for solid, L is for liquid, G is for gas, and aqueous, is for a solution with water. Chemical equations generally represent chemical changes, such as the second equation below. 2 potassium chlorates produce 2 potassium chlorides and 3 oxygens when they are heated. They can also represent physical changes. H2O solid, that is ice, add some heat and you get H2O liquid, water. Well, let's go back to this example of the hydrogen plus oxygen makes water. And again, as I stated before, there are 2 oxygens on the left-hand side and 1 on the right. So we need to balance these such that all the reactants match all the products in the numbers and kinds of atoms present. Here is the balanced equation. Double the number of hydrogens so that there are 4 hydrogens, plus the 2 oxygens from the O2 gives us 2 water molecules containing a total of 4 hydrogens and 2 oxygens. So for balancing chemical equations, there are a few things that we need to take into account. First of all, write the correct formula for the reactants on the left-hand side and for the products on the right-hand side. If you don't have correct formulas, kind of hard to balance. So we're going to work with this. Ethane reacts with oxygen to form carbon dioxide and water. And the formula for ethane is C2H6. And as you can see, it is definitely not balanced. We are going to change the numbers in front of the formulas, that is the coefficients, to make the number of atoms of each element the same on both sides of the equation. Do not change subscripts, because that changes the chemical compound. Start by balancing those elements that appear in only one reactant and one product. For example, below, carbon appears in ethane and carbon dioxide. We could start there. Hydrogen appears in ethane and water. We could start there. However, the oxygen appears in the reactant side in one chemical species, but on the product side appears in two different compounds, carbon dioxide and water. If polyatomic ions are present in both the reactants and the products, treat the polyatomic ion as a unit. This will make balancing easier. If the effect of balancing one element makes a previous element unbalanced, just go back and rebalance. So moving on with the combustion of ethane, there are 2 carbons on the reactant side, 1 carbon on the product side. We're simply going to double the number of carbons on the product side so that there are now 2 on each side. Next, we're going to move on to the hydrogen. There are 6 atoms of hydrogen on the reactant side and only 2 on the product side. So to make them equal, we put a 3 coefficient in front of the water, giving us 6 total hydrogen atoms. And because the hydrogen balancing does not affect the previously balanced carbon, we don't have to go back and rebalance the carbon. And finally, we're going to balance elements that appear in 2 or more reactants or products. In this case, we're going to balance oxygen. There are 2 oxygens on the left, and on the right side, carbon dioxide contributes a total of 4 oxygens. Water contributes a total of 3 oxygens for a total of 7. Taking 7 and dividing by 2, we get 7/2 or 3.5. We could leave it this way. However, working with stoichiometry problems, we prefer to have whole numbers. The solution to this is to multiply the entire equation by 2. Once everything is multiplied by 2, there are 2 ethanes, 7 oxygens, 4 carbon dioxides, and 6 waters total. So is it balanced? Well, let's take a look at that. 4 carbons on the reactant side, 4 carbons on the product side. 12 hydrogens on the reactant side, 12 hydrogens on the product side. 14 oxygens on the reactant side, and 14 oxygens on the product side. To see this visually, here's some pictures. The ethane molecules, the oxygen molecules, carbon dioxide, and water. And you could simply count or cross off to verify that the counts come out correctly. For example here, we could cross out the hydrogens. Hydrogens balance out. Carbons. 1, 2, 3, 4. 1, 2, 3, 4. Oxygens. 1, 2. 1, 2. 1, 2. 1, 2. 1, 2. 1, 2. And finally, 1, 2. Stoichiometry is using balanced chemical equations to find amounts. How do the amounts compare in the reaction below? In the equation, we see that 2 moles of ammonia, NH3, react with 1 mole of carbon dioxide to produce 1 mole of urea, NH2,2CO, and 1 mole of water. So what does this mean? We can just look at it as a long set of ratios. For example, you need 2 moles of ammonia for every 1 mole of carbon dioxide in the reaction. You need 2 moles of ammonia to produce 1 mole of urea in every reaction. You need 1 mole of carbon dioxide to produce 1 mole of water. 1 mole of water is produced from 2 moles of ammonia. These ratios will be used as conversion factors when we get to stoichiometry. And here's a large stoichiometry map or road map. Basically, what it shows is here on the left-hand side are not the reactants. On the left-hand side are the known compound or compounds. We have some value for gas laws or concentration or mass or atoms. On the right-hand side of the road map are the unknowns. And here we can produce atoms, mass, concentration, or gas laws. So we could actually go from reactant to reactant, reactant to product, product to reactant, or product to product. These are the 4 possibilities. So this lets you know that we don't inherently follow the reaction, reactants to products. First, let's look at the middle of the stoichiometry roadmap, which is the mole-to-mole portion. This will help us learn how to use the ratio, the molar ratio. How many moles of urea can be formed from 3.5 moles of ammonia? And here's the equation. The strategy is to go from moles of the known, 3.5 moles of ammonia, that's the known, 2 moles of urea, which is the unknown. So we're going to start off with the 3.5 moles of ammonia, multiply it by the molar ratio to get the number of moles of urea. The molar ratio, generically, the numerator is the coefficient of the unknown, and the denominator has in it the coefficient of the known. And in doing this, the units of moles of ammonia cancel out, leaving moles of urea. Next, we're going to take moles and go to mass. This is going to be a two-step process. What is the mass of urea? So this is the unknown. So over here, this is the unknown side. Made from a complete reaction of 3.74 moles of carbon dioxide. That is the known side. And as you can see, we have two arrows here. We got two steps to make. Start off moles of CO2, 3.74. Going to multiply that by 1 mole CO2 in the denominator, 1 mole urea in the numerator, and then we're going to put in the molar mass of urea, which I'm looking up right now. The molar mass of urea is 60.056 grams per mole. So 60.056 grams of urea per 1 mole urea. So now we just simply multiply through to get our answer. The answer on the calculator comes out to 224.60944, but remember we have to account for significant figures. The moles of carbon dioxide only has 3 significant figures, so the answer is 224 grams urea. And to confirm that we're on the right track, the moles of carbon dioxide cancel, moles of urea cancel, leaving us with mass of urea. The next problem, we're going to go from mass to moles. How many moles of carbon dioxide, unknown, are needed to react with 2.68 grams of ammonia, the known side? And note here that both carbon dioxide and ammonia are reactants. So the first step, 2.68 grams ammonia, has to be converted to moles, so we have to use the molar mass. So in effect, we are dividing by the molar mass. And then the second step is to use the molar ratio between ammonia and carbon dioxide. Ammonia goes in the denominator, and carbon dioxide, being the unknown, goes in the numerator. The answer comes out to be 0.0786847. Taking into account significant figures, we need 3, 0.0, 787 moles CO2. Lastly, we're going to do a total 3-step stoichiometry problem, starting out with the mass of a known and calculating a mass of an unknown. So a chemist basically wants to acquire 58.75 grams of urea. This is the known side. How many grams of ammonia are needed to produce that amount? So the strategy here is to go from mass of urea to moles of urea using the molar mass, going from moles of urea to moles of ammonia using the stoichiometric ratios, and finally using the molar mass of ammonia, calculate the mass of ammonia. So 58.75 grams urea, which is a product, divided by basically its molar mass, so that's step 1. Step 2, we're going to use the molar ratio, which is 1 mole urea and 2 moles ammonia. The last step is to take moles of ammonia to mass of ammonia using the molar mass of ammonia. And the answer is, to the correct number of significant figures, 33.32 grams ammonia. Now we're going to get a little bit more complex. Limiting reactant problems. The limiting reactant is the one that is used up first in a reaction. Basically, it limits the amount of the product that you can get. The excess reactant is the one that is left over. And to note, industry often makes the more expensive reactant the limiting one to ensure its completion of complete conversion into products, making it most efficient and cost effective. Finding the limiting reactant generally is a process involving 2 paths through the roadmap. So we're going to go 2 times through the roadmap to determine the limiting reactant. Once we know the excess reactant, we may or may not take an additional path through the roadmap. So a complete problem would be to use the roadmap to help us find the limiting reactant by going through it 2 times and then going through it 1 more time to find out how much there is of excess reactant. One note here, reactant is often used synonymously with reagent. So if you hear the term limiting reagent, it's the same. So this is an example of a limiting reactant problem based upon a sandwich. If you have a loaf of bread and has 16 slices of bread, you have a package of lunch meat, 10 slices of turkey, how many sandwiches can you make using 2 pieces of bread and 1 slice of meat? Well, you can probably see this in your own mind. You're going to run out of bread first after you make 8 sandwiches. You cannot continue to make 10 sandwiches. Thus, you can make 8 sandwiches, and the limiting reactant is bread. The excess reactant is turkey. We'll use 8 slices of turkey, and there will be 2 left over. And here's the visual of that, putting all the pieces together. So it also tells us how the comparison is going to go in our limiting reactant problems, and why we have 2 paths through the roadmap. The first path will take one of the reactants as the known to give us products. Here we can make 8 sandwiches. The second path through the roadmap will take us through the other reactant to product. And here, if we had enough bread, we could make 10 sandwiches. The lesser of the two, 8, is how many we can produce. And the bread is the limiting reactant. These 2 slices that are left over are the excess for the excess reactant. And since this is simplistic, we can know that 8 pieces of turkey are going to be used, and we subtract 8 from 10. But we would, in a chemical sense, go through the roadmap one more time, going from the limiting reactant, here it's bread, down to the turkey, find out how much turkey is used, and then subtract it from the amount of turkey started out with. In order to be able to identify a limiting reactant problem, you have to be able to realize that there are 2 amounts given for reactants. And the question will also ask for how much is produced for one of the products. So as it says down here, both reactant amounts are given and a product amount is requested. There may be more than 2 reactants, so there may be more than 2 amounts given. However, that is generally not the case. If there's only 1 reactant, you can't have a limiting reactant problem because it is the limiting reactant. There are a couple of other clues for limiting reactant problem. It might simply just ask, what is the limiting reactant? Just as simple as that. Or if you have two reactants and it says that one of the reactants is in excess, that's a problem wherein the other is the limiting reactant, and you don't have to worry about having a limiting reactant problem, but because the excess reactant is already identified for you. So identifying the limiting reactant. Start off with a balanced chemical equation. Convert the amount of each reactant to moles of the desired product, as stated in the problem. Compare the moles of the product from each reactant. The reactant that produces the smallest number of moles is limiting. You can also finish the conversion rather than convert moles from the limiting reactant to the desired units. You don't have to wait to the end to do that. You can do that as part of step 3. So here's an example. We want to know how many moles of water are formed when 0.75 grams of hydrogen gas react with 5 grams of oxygen. So here you absolutely have to turn off that kindergarten brain, because 0.75 is less than 5, but that does not mean that hydrogen is the limiting reactant. As a matter of fact, I set up this problem so it wouldn't be, to demonstrate that. So step 1, balanced chemical reaction. Step 2, 0.75 grams of hydrogen divided by the molar mass. Multiply it by the mole ratio of 2 moles of hydrogen to 2 moles of water to 2 moles of hydrogen, and you get 0.371 moles of water. 5 grams of H2O divided by 32 grams per mole times 2 moles of water per 1 mole of oxygen gives 0.313 moles of water, which is less than 0.371. Therefore, oxygen is the limiting reagent. Using the unrounded value for moles of water, we can finish, because the question asks for how many molecules. To go from moles to molecules, use Avogadro's number. 0.3125 moles of water times Avogadro's number gives us the answer of 1.88 times 10 to the 23rd molecules of hydrogen. We can also ask how many grams of hydrogen are left in excess. There are several different approaches that can be taken to this problem, but the one I like best is to take the limiting reactant to calculate the amount of the excess reactant used. So here we have 5 grams of oxygen. Divide it by its molar mass. Multiply it by the mole ratio, which is 2 moles hydrogen, 1 mole oxygen. Multiply that by the molar mass of hydrogen to get 0.631 grams of hydrogen used. To calculate the excess, take the initial amount, 0.750 grams of hydrogen, subtract the used amount, 0.631 grams of hydrogen, and you find you have 0.119 grams of hydrogen in excess. Yields. The theoretical yield is the maximum amount of product you can get as predicted by stoichiometry. In a limiting reactant problem, it occurs when the limiting reagent is used up and the amount that it produces. In other problems where you don't have a limiting reagent, it is the maximum amount that could possibly be produced. The actual yield is the amount that is produced in the laboratory setting. And finally, the percent yield is the ratio of the actual yield to the theoretical yield and tells us about the efficiency of the reaction. The equation is below. And here's a problem. Student is given 3.7 grams of zinc, which the student then reacts with excess hydrochloric acid and produces, at the end of the experiment, 1.58 grams of zinc chloride. What is the percent yield for this reaction? So the first thing to do is to calculate the theoretical yield. And again, we follow the same process. Mass of zinc divided by its molar mass times the molar ratio, which is 1:1, times the molar mass of zinc chloride to obtain 7.82 grams of zinc chloride, which, if all the zinc is used, that's what you should get. The percent yield then is 1.58 grams, how much you actually got, divided by 7.82 grams of zinc, which you should have gotten, multiplied by 100, which is 20.2%.